At the farthest edge of everything we can see, reality is built on a scale that defies human comprehension. We are about to journey to the very frontier of the observable universe to explore 30 unbelievable structures that challenge our most fundamental laws of physics. You will discover colossal walls of galaxies that stretch for billions of light years and mysterious voids of absolute nothingness, so vast they seem impossible. How did these cosmic giants form from a nearly uniform beginning, and what do they reveal about the fate of our entire universe? By the end of this exploration, you will see the cosmos not as a random scattering of stars, but as a structured, evolving architecture of breathtaking grandeur. What do you believe is the most profound mystery waiting for us in the deep cosmos? Our entire visible cosmos exists within a vast sphere centered on us, a bubble of reality with a radius of staggering proportions, about 46.5 billion light years. This is not a physical wall you could ever touch. It is the ultimate frontier of information, a horizon created by the simple, unbreakable rule that light has a finite speed and the universe has a finite age. Everything we can possibly see, from the glow of the screen in front of you to the most distant galaxy, lies within this sphere. The light from objects at this very edge has been traveling for nearly the entire age of the cosmos, over 13 billion years, just to reach our telescopes now. Yet the universe has been expanding all that time, stretching the fabric of space itself, which is why the object that emitted that ancient light is now actually 46 billion light years away. This boundary is our particle horizon, the limit of all the light and information that has had time to reach us. Beyond it, there is a deeper boundary, the cosmological event horizon. This is the point beyond which, even if we waited for an eternity, light from galaxies receding due to the universe's expansion could never, ever reach us. They are forever lost to our view, their stories untold. Cosmologist Janna Levin frames this not as a limit of space, but as a limit of time and knowledge. We are prisoners of the present moment, able to observe only a fraction of the total cosmos. Grasping this concept is the first, crucial step. It redefines the edge not as a distant place, but as a moment in our own past, setting the stage for the cosmic giants that inhabit this final frontier. This cosmic horizon is not an empty frontier. It is populated by titans. Lying within the depths of our observable sphere is a structure of such staggering scale that its discovery sent ripples through the world of cosmology, a filament of galaxies known as the Hercules-Corona Borealis Great Wall. To grasp its size, you must first try to visualize a single thread woven through the fabric of the universe, a thread so long that light itself would take over 10 billion years to travel from one end to the other. This is not merely a large grouping of galaxies. It is a cosmic continent, a connected web of galaxy clusters and dark matter that defies our expectations of how the universe should be arranged. For a long time, a foundational rule in cosmology, called the cosmological principle, suggested that if you zoomed out far enough, the universe would look roughly the same in every direction. Matter would be evenly distributed, with no single structure claiming dominance. The Hercules-Corona Borealis Great Wall shatters that assumption. Its sheer existence challenges the very definition of uniformity on the largest scales. How was such a leviathan found? The key was not in mapping individual, faint galaxies at such immense distances, but in observing the violent, brilliant deaths of massive stars. Astronomers, led by John Hackilla, began mapping the locations of gamma-ray bursts. These are the most energetic explosions in the universe, and they act like cosmic flashbulbs, briefly illuminating their host galaxies. When they plotted these bursts across the sky, a pattern emerged, a shocking concentration of events that traced the outline of this previously invisible wall. The scale of this structure pushes against theoretical limits. Cosmological models, which are informed by the subtle patterns in the cosmic microwave background radiation, have calculations for just how large a single structure should be able to grow under the influence of gravity over the universe's lifetime. The Hercules-Corona Borealis Great Wall appears to be brushing right up against, or perhaps even exceeding, that theoretical maximum size. Its presence forces scientists to re-examine the models of large-scale structure formation and the powerful, invisible influence of dark matter that guides this cosmic architecture. This gargantuan filament serves as a stunning introduction, a first glimpse of the architectural marvels that populate the cosmic frontier, and it is merely the beginning of our journey into the realm of the impossible. Yet the universe often hides its grandest designs in plain sight. While the Hercules-Corona Borealis Great Wall lies at the very edge of perception, another colossal structure resides much closer to home, a galactic megalopolis known as the Sloane Great Wall. Discovered through the meticulous mapping of the Sloane Digital Sky Survey, this structure is a sprawling network of galaxies stretching for approximately 1.37 billion light-years. To call it a wall is almost an understatement. It is a vast cosmic continent, a web of interconnected superclusters that forms one of the largest known structures in the entire observable universe. Its relative proximity to us offers a unique, high-definition view of the universe's architecture. Within its immense borders lies the Shapley concentration, one of the most massive collections of galaxies we have ever identified. Astronomer J. Richard Gott noted that the Sloane Great Wall provided some of the most compelling early evidence for the filamentary nature of the cosmos. It showed us that galaxies are not scattered randomly but are strung along invisible threads of dark matter like pearls on a necklace, gathering at the intersections in dense, brilliant knots. This intricate design is a frozen record of the gravitational forces that have sculpted the universe for billions of years. By studying its detailed structure, we can trace the history of galaxy formation and clustering with unprecedented clarity. The Sloane Great Wall acts as a nearby laboratory, revealing the fundamental processes that build the cosmos. But if these vast walls of light represent the dense urban centers of the universe, what lies in the empty spaces between them? The answer leads us to a paradox far stranger than any structure. Between these brilliant walls of galaxies lies the opposite extreme, a realm of profound emptiness known as the Bootes Void. This is a spherical region of space spanning 330 million light-years, a volume so vast it could contain thousands of galaxies like our Milky Way, and yet it holds almost none. Its discovery in the 1980s by astronomer Robert Kirshner and his team was a shock to the scientific community. Instead of the expected, roughly even distribution of matter, they found a staggering nothingness, a cosmic desert of unparalleled scale. Kirshner described the experience as deeply unsettling, a feeling of looking into an abyss that fundamentally contradicted the picture of a uniformly filled cosmos. How could such a vacuum exist? The leading theories are as fascinating as the void itself. One possibility is that the Bootes Void is not a single, pristine emptiness, but the result of a cosmic merger. Over billions of years, smaller voids, like soap bubbles in a froth, could have coalesced, their walls dissolving to create one giant, hollow sphere. Another, more profound idea is that this region was simply born different, a part of the primordial universe that started with a slight deficit of matter. As the cosmos expanded, that initial small emptiness was stretched into the colossal void we detect today. This profound absence of structure is as telling as the presence of the Great Walls. It forces us to confront the true texture of the universe, a sponge-like structure of dense filaments surrounding immense, dark bubbles. What other voids of such scale might be lurking in the unseen darkness? And what does this cosmic emptiness tell us about the forces that shape reality itself? The answer leads us to an even more immense and mysterious kind of structure, one defined not by what is there, but by the ghostly imprint of what is missing. The emptiness of the boot's void is a profound statement, but the cosmos is also capable of statements of pure, concentrated power. We find one such declaration in a structure known as the Huge Large Quasar Group, or Huge LQG. This is not a wall of ordinary galaxies, but a colossal gathering of quasars, the universe's most brilliant and violent beacons. Each quasar is the intensely active nucleus of a distant galaxy, powered by a ravenous supermassive black hole. When matter falls into this gravitational trap, it heats to incredible temperatures, outshining the galaxy's billions of stars to become a lighthouse visible across the cosmos. The huge LQG is a city of these lighthouses, a cluster of them spanning an almost unthinkable 4 billion light-years. Its discovery, led by cosmologist Roger Clouse, was a statistical shock. The cosmological principle, which posits a roughly uniform universe on the grandest scales, suggests that such a massive concentration of quasars should be virtually impossible. The probability of finding this specific grouping by pure chance is astronomically low, like rolling a die and getting the same number 100 times in a row. This structure's very existence pushes directly against our understanding of cosmic homogeneity. What does it mean for a structure of this scale to exist? It suggests that the seeds of its formation were planted in the very earliest moments of the universe, imprinted as subtle variations in density that gravity then amplified over billions of years into this titanic gathering. The intense energy output of these quasars, all residing relatively close to one another on the cosmic web, also presents a puzzle. Their collective radiation and winds could have fundamentally altered the evolution of an entire region of space, perhaps even preventing the formation of new galaxies by blowing away the raw gas needed for their birth. The huge LQG is more than just a record-breaking object. It is a direct challenge, its brilliant fury forcing us to question if we have truly seen the upper limits of cosmic structure. This luminous anomaly naturally pulls our attention to other extreme objects that defy simple categorization, guiding us toward the most energetic and enigmatic phenomena in the known universe. Even brilliant quasars must eventually fade, but the universe preserves its deepest secrets in a far more ancient and subtle form. We now turn to the oldest light in existence, the cosmic microwave background radiation. This faint afterglow from the Big Bang fills all of space, a nearly uniform tapestry of warmth. Yet woven into this fabric is a puzzling anomaly, a region of profound cold known simply as the cold spot. This is not merely a random fluctuation. It is a vast circular patch of sky that is significantly colder than the average, a chilling imprint from the universe's infancy. For cosmologist Laura Mersini-Horton, this anomaly is a potential crack in the wall of our reality. One compelling theory suggests this cold spot is the ghostly bruise from a collision with another universe in the vast multiverse. In this scenario, our infant cosmos may have bumped against a neighboring bubble of spacetime, an interaction that drained energy from that region and left it forever cold. The alternative explanation is almost as strange. It could be a shadow cast by an immense supervoid, a vacuum of matter so vast that light loses energy as it travels through this cosmic emptiness, creating a cold imprint in the background radiation. The problem is that surveys have failed to find a void large enough to explain the cold spot's profound chill. This leaves the collision hypothesis as a tantalizing possibility, a potential piece of evidence for a reality beyond our own. The cold spot stands as a cosmic fossil, a preserved relic from the first moments of everything. Its very existence challenges the standard model of cosmic inflation, which predicts a more uniform universe. This mysterious cold patch forces us to ask if we are truly alone in the cosmos, or if our universe is just one island in an infinite sea of other realities. What other subtle fingerprints from beyond our horizon might be hidden within this ancient light, waiting to be decoded? The universe seems to prefer grand, sweeping gestures, and one of its most elegant is a structure called the Giant Arc. Stretching across an incredible 3.3 billion light-years, this formation is a near-perfect curve of galaxies, a celestial crescent etched onto the fabric of space. Its discovery by astronomer Alexia Lopez was a masterstroke of cosmic cartography. She did not simply look for the galaxies themselves, which are faint at such distances. Instead, she used the brilliant light of even more distant quasars as a cosmic flashlight. As this light traveled for billions of years towards Earth, it passed through clouds of magnesium gas associated with unseen galaxies. By analyzing how the quasar light was absorbed, Lopez could map the positions of these galaxies, revealing a pattern that had been invisible to direct observation. What emerged was not a chaotic cluster, but a graceful, almost symmetrical arc. This elegant shape is a profound puzzle. Our current models of cosmic evolution, driven by the chaotic forces of gravity and dark matter, tend to produce more web-like filamentary structures, not vast, coordinated curves. The giant arc's graceful symmetry suggests something else might be at work. It hints that the universe, on its very largest scales, might not be the same in every direction as we once believed. There could be a preferred direction, a fundamental grain or texture to spacetime that guided matter into this beautiful, impossible form. How could gravity alone create such a precise, sweeping architecture? The giant arc stands as a quiet but formidable challenge to our understanding, a cosmic question mark written in starlight. It compels us to search the skies for other geometric patterns, wondering if circles, rings, or even more complex shapes are hidden in the deep field, waiting to reveal a new layer of order in the apparent chaos of the cosmos. These graceful arcs and vast walls are woven into a structure even grander, a flowing superhighway of galaxies that contains our own cosmic home. We are all residents of the Laniakea Supercluster, a celestial continent whose name means immense heaven. This structure, spanning 520 million light-years, redefined our understanding of where we live. For decades, we saw our local group of galaxies as a small, isolated neighborhood. Laniakea reveals we are part of a sprawling metropolis, a web of 100,000 galaxies all moving together in a slow, cosmic river. The key to discovering this supercluster was not just mapping where galaxies are, but watching how they move. Astronomer R. Brent Tully and his team meticulously charted the velocities of galaxies, tracing the subtle currents flowing through the darkness. They found that our entire local universe is drifting toward a single, powerful gravitational focal point hidden behind the dust of our own Milky Way, a mysterious region we call the Great Attractor. Imagine a vast watershed where every stream and river eventually flows toward a single, distant sea. Laniakea is our cosmic watershed, and every galaxy within its borders, including our own, is flowing toward that same unseen destination. This movement reveals the hidden skeleton of the cosmos, the underlying scaffolding of dark matter that dictates the motion of everything we can see. Knowing we are part of Laniakea transforms our perspective. We are not on a lonely island, but on a leaf floating in a vast, gentle river, a river whose currents were set in motion by the gravitational pull of the entire supercluster. This local context is vital, for it provides the starting point from which we can truly comprehend the scale of the even larger giants that lie beyond our immediate horizon. This cosmic watershed, Laniakea, is itself just one thread in a far grander tapestry. At a scale that dwarfs even our immense supercluster, we find the Pisces Cetus Supercluster complex, a sprawling network of galactic filaments that spans over 1 billion light-years. This is not a single object, but a vast cosmic metropolis, a web of interconnected superclusters and the dark voids that separate them. It serves as a perfect grand-scale model of the universe's true architecture, the cosmic web in all its intricate glory. Within this complex, galaxies are not scattered randomly. They are strung along invisible rivers of dark matter, flowing along these filaments like water through a system of interconnected canals. The great voids between them are the empty ocean basins, the cosmic deserts where matter is sparse. This revolutionary view of the universe as a structured web was brought into sharp focus by the pioneering work of cosmologist Margaret Geller and her colleagues. Their groundbreaking maps of the cosmos, created through painstaking surveys, revealed for the first time that the universe on its largest scales is not a formless soup, but a sponge-like structure of immense filaments and bubbles. The Pisces Cetus complex is a direct result of gravity's patient work over billions of years. Tiny, quantum fluctuations in the density of the primordial universe were amplified by gravity, with slightly denser regions pulling in more and more matter. Over cosmic time, this process drew matter into the vast, interconnected threads we observe today, leaving behind the empty expanses of the voids. The most fascinating parts of this web are the nodes, the intersections where multiple filaments cross. Here, gravity works overtime, piling galaxies upon galaxies to create the most massive structures in the universe, the immense galaxy clusters. These dense knots are the power centers of the cosmic web, where thousands of galaxies swarm in a relatively small volume, their collective gravity dictating the flow of the entire network. How does our own Laniakea fit into this billion light-year complex? We are likely just one neighborhood within its endless, flowing streets, our motion toward the Great Attractor merely a local expression of the complex's grander gravitational pull. This realization pushes our understanding of structure to a new extreme, forcing us to ask if even a web spanning a billion light-years is truly the final level of cosmic architecture. This gravitational river we are riding flows toward a singular, mysterious destination. For decades, astronomers have known our galactic neighborhood is not drifting aimlessly, but is caught in a vast, unseen current, pulled toward a specific point in the constellation Centaurus. They named this enigmatic focal point the Great Attractor. This is a region of space possessing a gravitational pull so immense that it is drawing our entire local universe, including the Laniakea Supercluster, toward it at a staggering speed of over 600 kilometers every single second. The central mystery, however, is that we cannot see it directly. Our view from within the Milky Way is blocked by the thick dust and stars of our own galaxy's central bulge, a region astronomers call the zone of avoidance. It is as if we are trying to see a magnificent city on the other side of a towering, opaque mountain range. We can feel its immense pull. We can measure its profound influence on the motion of thousands of galaxies, but its true face remains hidden. Initial observations suggested the mass of the Great Attractor was equivalent to tens of thousands of galaxies. But as our ability to peer through the cosmic dust improved, thanks to telescopes that can observe in infrared and radio wavelengths, a more complex picture emerged. The work of astronomers like Donald Lynden Bell revealed that the Great Attractor is not a single, monstrous object. It appears to be the core of our local supercluster, a massive knot in the cosmic web where the density of galaxies and the dark matter that binds them reaches an extraordinary peak. Yet, even this colossal concentration of mass may not be the full story. The motion of our entire supercluster suggests there might be something even larger and more distant pulling us, a structure beyond the Great Attractor known as the Shapley Attractor. This transforms the Great Attractor from a final destination into a waypoint on a much longer cosmic journey. Its enduring mystery exemplifies a profound truth about exploring the cosmos. The most powerful forces shaping our universe often remain hidden, their presence known only by the subtle, irresistible currents they create in the sea of spacetime. What other invisible titans are guiding these cosmic flows from the shadows? This gravitational journey through the cosmic web reveals a startling truth about our own location. We are not residents of a dense galactic metropolis, but live inside a cosmic bubble, a vast and relatively empty region of space known as the KBC Void. Named for the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie who proposed its existence, this void is an immense spherical region approximately 2 billion light-years across where the density of galaxies is significantly lower than the cosmic average. Our Milky Way galaxy, along with our entire local group, sits near the center of this underdensity. This is not a perfect vacuum like the Boots Void, but it is a genuine cosmic suburb, a sparse neighborhood on the grand scale of the universe. The implications of our location inside this bubble are profound, especially for our most fundamental cosmic measurements. One of the most critical numbers in cosmology is the Hubble constant, which describes the current rate of the universe's expansion. When we measure this expansion from within our local void, we are essentially looking outward from a region with weaker gravity. Since there is less mass pulling on galaxies from our local environment, those galaxies appear to be receding from us at a slightly faster rate than they would if we were in an average region of space. This local perspective could be subtly skewing our measurements, potentially contributing to the ongoing tension between different methods of calculating the Hubble constant. Similarly, our understanding of dark energy, the mysterious force driving cosmic acceleration, is also filtered through this lens. If we incorrectly assume our local environment is typical, we might be misinterpreting the data, mistaking the effects of our local emptiness for the global influence of dark energy. Living inside the KBC Void forces a cosmic humility upon us. It reminds us that our viewpoint is not a privileged, average one, but is uniquely local and potentially biased. This realization prepares us to fully appreciate the true scale of emptiness that exists beyond our bubble, the even larger voids that define the stark contrasts of the cosmic web. The discovery of our own cosmic bubble was only possible because of a much earlier revelation, one that shattered the long-held belief in a perfectly smooth cosmos. Decades before we mapped Laniakea or probed the KBC Void, astronomers Margaret Geller and John Huckra unveiled a structure that would forever change our cosmic perspective, the CFA2 Great Wall. This was not just another cluster of galaxies, it was a colossal filament stretching for 500 million light-years, one of the first true walls of galaxies ever identified. Its existence came to light through the pioneering Center for Astrophysics Redshift Survey, a project that meticulously measured the distances to thousands of galaxies. When Geller and Huckra plotted their data in 3 dimensions, a stunning pattern emerged from the noise. Instead of a random, homogeneous scatter, the galaxies were arranged in a vast, interconnected sheet, a great wall defining an entire sector of the nearby universe. The visual impact was immediate and profound. It provided the first clear, undeniable evidence that the universe on large scales is not smooth, but fundamentally lumpy and structured. This was a landmark moment, a turning point in cosmology. The CFA2 wall showed that galaxies are the bricks and mortar of a grander architecture, gathering into immense continental structures separated by vast voids. That initial map was like a small window suddenly opening onto a previously hidden city, revealing streets and neighborhoods where we had only seen isolated lights. This pioneering discovery did more than just catalog a single object. It fundamentally rewrote the rules of cosmic cartography. It proved that such immense structures were not rare anomalies, but common features of the cosmos, setting the stage for the hunt to find even larger and more distant walls. The CFA2 Great Wall stands as a monument to scientific curiosity, the first giant whose discovery taught us to look for the patterns in the celestial tapestry, a lesson that would soon lead us to structures of truly unimaginable scale. Far to the south, a celestial counterpart mirrors the grand architecture of the north. The southern wall rises from the depths of the southern sky, a vast filament of galaxies discovered through immense redshift surveys. It serves as the southern hemisphere's answer to the Sloane Great Wall, a colossal structure that reinforces a profound cosmic truth. While local regions may be dominated by immense voids or dense clusters, when you zoom out to the grandest scales, the universe begins to display a remarkable statistical symmetry. The existence of such a massive, mirrored feature in the south tells us that the fundamental processes of cosmic construction operate the same way everywhere. This is not a coincidence. It is a direct result of the uniform laws of physics and the nearly identical initial conditions that prevailed across the infant cosmos. The presence of the southern wall provides powerful, observable evidence for the cosmological principle, the idea that the universe has no single preferred location or direction. Its intricate, filamentary shape is a perfect match for the web-like structures we see in the north, woven from the same threads of dark matter and lit by the same brilliant galaxies. This mirroring encourages astronomers to look for other symmetrical patterns, to see the cosmos not as a chaotic jumble, but as a tapestry woven with a consistent, repeating design. If such immense walls can be found in opposite parts of the sky, what other echoes of order are waiting to be discovered in the deep field, hidden within the apparent chaos of the cosmic web? This celestial geometry defies all expectations of cosmic chaos. We find ourselves confronting the giant gamma-ray burst ring, a formation so vast and so perfectly circular it seems almost artificial. Imagine a circle drawn onto the sky with a diameter of 5.6 billion light-years, a hoop so immense it could encircle a significant portion of the observable universe. What makes this ring visible are not galaxies, but the brief, violent deaths of massive stars. This structure is traced by a series of gamma-ray bursts, the most powerful explosions known to exist. Each burst is a final, catastrophic flash from a star, a cosmic beacon that for a few seconds outshines an entire galaxy. According to our best models, these cataclysmic events should be scattered randomly across the cosmos, like flashes of lightning in a storm. The probability of them aligning by pure chance to form a near-perfect circle is astronomically low, akin to rolling a handful of dice and having them land to spell out a sentence. The discovery, led by astronomer Lajos Balazs, was a statistical shock. His team was analyzing the positions of known gamma-ray bursts when this impossible pattern emerged from the data. One theory suggests we are not looking at a flat ring at all, but the two-dimensional projection of a three-dimensional spherical shell. In this scenario, a titanic, primordial sound wave might have rippled through the early universe, compressing matter into a vast bubble. The galaxies that formed on this shell's surface would then, billions of years later, produce the gamma-ray bursts that trace its outline for us to see. Another, even more exotic possibility involves cosmic strings. These are hypothetical, one-dimensional defects in the fabric of space-time, relics from the universe's first moments of existence. Think of them as incredibly thin, unimaginably dense cracks in reality, thinner than an atom but with the mass of a galaxy. If a cosmic string existed, its immense gravitational pull could have drawn matter into a perfect circular structure around it. The existence of this ring forces us to question the very randomness of the cosmos. Are we seeing a flaw in our statistical methods, or a genuine crack in our cosmological principles? This circular enigma points toward a universe that might be filled with other geometric formations, hidden patterns of order waiting to be discovered in the chaos of deep space. This mysterious streaming motion of galaxy clusters presents a challenge that reaches beyond our cosmic horizon. Astronomer Alexander Kashlinsky and his team made a startling discovery while studying the motion of massive galaxy clusters. They found these immense structures were all moving in a coherent stream, not just with the general expansion of the universe, but in a specific, shared direction at incredible speeds. This phenomenon was named the dark flow. It is as if an unseen river is pulling everything along a path that points toward the constellations Centaurus and Hydra. The most baffling part is that the source of this pull cannot be located within the 46 billion light-year sphere of our observable universe. The gravitational force required to create such a coordinated motion is immense, suggesting the presence of a supermassive structure, a cosmic attractor of unimaginable scale that lies beyond our particle horizon. One profound explanation is that this flow is a remnant from the epoch of cosmic inflation, a gravitational tug from a region of space that became forever separated from our own as the universe expanded faster than light. This would mean the structure influencing us is not just far away, but fundamentally outside our cosmic bubble, in a domain we can never observe. Another, even more mind-bending possibility is that the dark flow is evidence of a gravitational pull from another universe entirely, a neighboring bubble in a vast multiverse. The existence of such a flow directly challenges the cosmological principle, suggesting that the universe on its very largest scales we cannot see, is not uniform after all. It hints that our entire cosmos might be tilted, pulled by the gravity of something truly other. The dark flow is more than just a curious motion. It is a ghostly current, the only clue we have to the architecture of the unobservable. What other invisible forces are guiding our journey through the multiverse? Their presence felt only as a silent, relentless pull in the darkness. This silent, relentless pull hints at a cosmos far larger than we can see, raising a profound question about its ultimate texture. Is the universe on its grandest scales truly smooth and uniform, or is it an endless hierarchy of structures within structures? This brings us to a fundamental cosmic concept known as the end of greatness. It is the theoretical scale, thought to be around 300 million light-years, where the clumpy, filamentary nature of the cosmic web is finally supposed to fade into a featureless, homogeneous background. Imagine looking at a forest from a high-flying airplane. Up close, you see individual trees, then clusters of trees, and then entire groves. But from a great enough height, the forest blends into a single, continuous green carpet, with no single tree or grove standing out. The end of greatness is that theoretical viewing altitude for the entire universe. Cosmologist James Peebles has long championed this idea as a cornerstone of the standard cosmological model. It represents the final transition, the point where the universe's initial, nearly smooth state reasserts itself, and the intricate architecture woven by gravity finally dissolves into statistical uniformity. This concept is not just a philosophical idea, it is a practical boundary that defines how we build our models of cosmic evolution. It tells us that there should be a maximum size for any single structure, a scale beyond which nothing larger can coherently form. Yet, the titans we have already encountered, like the Hercules-Corona Borealis Great Wall spanning 10 billion light-years, stand in direct defiance of this theoretical limit. Their sheer existence suggests that the end of greatness might be a horizon that retreats as we advance, a boundary that is far more distant and complex than we once believed. If structures can exist that are dozens of times larger than the proposed transition scale, what does that say about the initial conditions of the universe or the enduring power of dark matter to sculpt reality? The search for the largest possible structure becomes a direct test of one of cosmology's most basic assumptions, pushing us to ask if there is, in fact, any end to the universe's architectural ambition at all. But the cosmic web was not built in a day. To witness its raw beginnings, we must journey back through time to an era just 2.3 billion years after the Big Bang. Here we find a cosmic embryo, a sprawling, chaotic structure known as the Hyperion Proto Supercluster. This is not the neat, defined architecture of Laniakea, but a primordial giant caught in the act of formation. Discovered by a team using the VIMOS instrument on the Very Large Telescope, Hyperion holds the record as the largest and most massive proto-supercluster ever identified at such an immense distance. Its light has been traveling for over 11 billion years to reach us, showing us a universe in its tumultuous youth. Astronomer Olga Cucciotti, who led the discovery, described Hyperion's structure as complex and not yet settled into a single core. It is a teeming metropolis under construction, with at least 7 dense, bustling regions already visible, all connected by a web of nascent filaments of gas and dark matter. Observing Hyperion is like finding the blueprints for a future continent. It reveals that the gravitational processes which build the great walls and voids began their work with astonishing speed. The seeds of today's largest structures were planted in the universe's first 2 billion years, growing with a ferocity that challenges our models. How did such a colossal entity assemble itself so quickly after the dawn of time? The existence of this young giant forces us to reconsider the timeline of cosmic evolution, proving that the universe's ambition for grand design was present from the very start. This glimpse into the deep past compels us to look for other primordial formations, to trace the entire life story of the cosmic web from its first whispers to its present-day majesty. The cosmic ambition for grand design finds another stunning expression in the Saraswati Supercluster, a celestial empire of galaxies stretching over 600 million light-years. This is not a relic from the deep past, but a colossal structure residing a mere 4 billion light-years away, a relative stone's throw in cosmic terms. Its discovery by a team of Indian astronomers, with Joydeep Bagchi playing a key role, was a landmark achievement. They named it Saraswati, after the Hindu goddess of knowledge, music, and art, a fitting title for a structure that reveals so much about the universe's creative power. Saraswati is a true cosmic continent, a vast overdensity containing the mass of at least 43 massive galaxy clusters and several sprawling filaments, all held together by the invisible threads of dark matter. What makes Saraswati so remarkable is its epoch. It exists at a cosmic time when, according to many models, the accelerating expansion driven by dark energy should have begun to stifle the growth of such immense structures. The formation of something this massive and coherent so recently in the universe's history challenges our simulations. It suggests that the gravitational pull of dark matter was exceptionally potent in this region, allowing it to overcome the repulsive force of dark energy and continue its assembly into a modern-day giant. Saraswati is not a fossil, but a living, breathing metropolis, still actively gathering matter and galaxies into its gravitational embrace. Its very existence points toward a cosmos where even larger, more massive conglomerations might be taking shape right now, hidden in the depths of space, their final forms not yet fully revealed to our telescopes. These dense nodes of the cosmic web are not just abstract concepts, but tangible places of immense power and violence. The Coma Cluster stands as a perfect example, a colossal gravitational hub located approximately 320 million light-years from Earth. This is a place where the universe packs thousands of galaxies into a relatively small volume of space, creating a brilliant, chaotic metropolis. If the cosmic web is a city of filaments, then clusters like Coma are its downtown centers, the bustling intersections where everything comes together. It was here, in the 1930s, that the brilliant and often unorthodox astronomer Fritz Zwicky made a startling observation. By measuring the velocities of galaxies swirling within the cluster, he calculated that the visible mass of all those stars and gas clouds was vastly insufficient to provide the gravitational glue holding the cluster together. The galaxies were moving so fast that they should have flown apart, scattering into the void. Zwicky concluded that there must be a huge amount of unseen matter, which he called dunkle materie or dark matter, providing the missing gravity. His radical proposal was largely ignored for decades, but time has proven him right. The Coma Cluster became one of the first observational pillars for the existence of this invisible cosmic component. But dark matter is not the only secret this cluster holds. The space between the galaxies is not empty. It is filled with a superheated, thin gas known as the intracluster medium, with temperatures soaring to millions of degrees. This gas is so hot it emits powerful X-rays, painting the cluster in a high-energy glow that can only be seen with special telescopes. This seething plasma tells a story of violence, a history of galaxies being stripped of their own gas as they race through the cluster's core, their star-forming fuel ripped away by the relentless pressure. The Coma Cluster acts as a living laboratory, allowing us to watch how galaxies evolve in the most extreme environments. We see spiral galaxies having their beautiful arms shredded and transformed into bland, elliptical shapes, their stellar populations aging under the harsh conditions. Studying this dense node reveals the ultimate fate of galaxies drawn into such a powerful gravitational well, showing us the points where the cosmic web's architecture is at its most concentrated and dynamic. What other transformations occur within these brilliant, crowded hubs that anchor the entire structure of the universe? While massive clusters like Coma reveal broad cosmic laws, a much closer gathering offers a more intimate portrait of galactic life. The Fornax Cluster floats just 65 million light-years from Earth, a nearby metropolis of galaxies. Its relative proximity provides a high-resolution window into the daily dynamics of a dense environment, a place where we can study the subtle interactions between galaxies with stunning clarity. Fornax is not a single, monolithic entity, but a diverse community. Its core is dominated by giant elliptical galaxies, ancient spheres of aging stars that have largely exhausted their star-forming gas. Surrounding them are spiral galaxies, their graceful arms still rich with the blue glow of young stellar nurseries. This mix of types makes Fornax a perfect laboratory for understanding how a galaxy's fate is sealed by its surroundings. The cluster's most famous resident is the barred spiral galaxy NGC 1365, a stunning pinwheel that appears to be orbiting the cluster's core. Its motion through the thin, hot gas that permeates the space between galaxies is stripping away its own interstellar material, a process known as ram pressure stripping. This effectively starves the galaxy of the fuel it needs to create new stars, slowly transforming it from a vibrant spiral into a quiescent, red and dead elliptical. We are witnessing galactic evolution in real time. The cluster is also a site of active mergers, where galaxies are captured by gravity and slowly torn apart, their stars flung into vast streams that eventually blend into the smooth halo of the dominant central galaxy. This slow cosmic dance, visible in intricate detail from our vantage point, shows us how the largest elliptical galaxies are built, one cannibalized neighbor at a time. Because it is so close, astronomers can resolve individual stars within its galaxies, studying their ages and compositions to piece together a detailed history of star formation and chemical enrichment. The Fornax Cluster is more than just a pretty sight. It is a nearby example of a universal process. It demonstrates that the violent transformations we infer in distant, massive clusters are happening quietly and constantly in our own cosmic backyard, revealing the relentless forces that sculpt all galactic cities. Our own galactic neighborhood is part of a grander design, the Virgo Supercluster. This sprawling collection of galaxy groups spanning 110 million light-years is our immediate cosmic home. At its heart lies the Virgo Cluster, a dense gathering of over 1,000 galaxies whose collective gravity acts as the central anchor for our entire region of space. Our own Milky Way, along with the Andromeda Galaxy and the rest of our local group, resides on the quiet outskirts of this supercluster, a suburban area far from the brilliant downtown core. The concept of this local supercluster was profoundly advanced by astronomer G. de Vaucouleurs, who championed the idea that the universe is not a simple collection of stars, but a hierarchy of structures. He saw that galaxies gather into groups, groups into clusters, and clusters into immense superclusters, a vision that laid the groundwork for our modern understanding of the cosmic web. This local context is vital. Our position within the Virgo Supercluster frames everything we see when we look out into the deeper cosmos. It is our baseline, the familiar territory from which we measure all other distances and motions. When we feel the mysterious pull of the Great Attractor or chart our course within the even larger Laniakea, we are experiencing the gravitational currents of a river system that begins right here in our own supercluster. Understanding Virgo is like studying the map of your own continent before embarking on a journey around the world. It provides the essential scale and perspective needed to comprehend the truly colossal architectures that lie beyond, reminding us that even our vast galaxy is but a single point of light in a sprawling local empire. Even our own galaxy can hide the most colossal neighbors from sight. Deep in the direction of the constellation Ophiuchus, the Serpent-bearer, lies a supercluster of almost unimaginable mass, a structure so vast it ranks among the most substantial conurbations of matter we have ever identified. Yet for centuries it remained completely invisible to us. The reason is a cosmic accident of placement. The Ophiuchus Supercluster sits directly behind the central bulge of our own Milky Way, a region so thick with interstellar dust and gas that it blots out the visible light from countless background galaxies. This phenomenon is called galactic extinction, and it creates a formidable blind spot in our maps of the cosmos. To uncover this hidden giant, astronomers had to look with different eyes. They turned to space-based observatories that detect X-rays. The space between galaxies in a massive cluster is not empty. It is filled with a superheated plasma that can reach temperatures of millions of degrees. This incredibly hot gas emits a torrent of X-ray energy, a form of light that can punch through the obscuring dust of our galaxy where visible light fails. By mapping the sky in X-rays, they revealed the brilliant glow of immense galaxy clusters within Ophiuchus, tracing the outline of the supercluster itself. One of its core components is the Ophiuchus Cluster, a gravitational titan containing thousands of galaxies. The study of this distant realm is a testament to technological ingenuity, a reminder that to see the universe clearly, we must often look beyond the narrow slice of reality visible to our human eyes. The existence of such a massive, hidden structure so relatively close to us in cosmic terms forces a humbling realization. Our deepest maps of the cosmos are still incomplete, with other colossal wonders likely waiting in the shadows, their presence known only by the subtle, high-energy whispers that manage to slip past the veil of our own galactic core. This immense gravitational pull we feel is not coming from a single point, but from a true cosmic empire. The Shapley Supercluster stands as the single greatest concentration of mass in our entire local universe, a gravitational titan located some 650 million light-years away. While the Great Attractor acts as a local waypoint, Shapley is the distant capital, the primary source of the mysterious current pulling our entire galactic neighborhood. Its discovery traces back to the pioneering work of Harlow Shapley, who first noted an unusual concentration of galaxies in this region of the sky. Decades of further observation have revealed a structure of almost unimaginable density, a sprawling megalopolis containing dozens of massive galaxy clusters, all bound together by their collective gravity. To stand at its center would be to see a sky perpetually ablaze with the combined light of tens of thousands of galaxies, a celestial city so vast it defies human comprehension. This supercluster's influence is not confined to its own borders. Its gravitational reach extends across the cosmic web, tugging on everything in its vicinity, including us. The peculiar motion of our local group, that 600 km/s drift we feel, is in large part a response to Shapley's immense call. It is the dominant force in the cosmic watershed that contains our own Laniakea Supercluster, the ultimate destination of the great river of galaxies we are all flowing along. The existence of such a massive concentration so relatively nearby presents a fascinating puzzle. How did so much matter accumulate in one place? It suggests that this region of the universe began with a primordial head start, a slight overdensity in the early cosmos that gravity relentlessly amplified over billions of years into this ultimate attractor. Shapley represents the pinnacle of what gravity can achieve, the final word in mass accumulation within our observable horizon. Its sheer dominance makes us wonder if other, even larger mass concentrations might lie just beyond our view, their invisible hands guiding the flows of entire superclusters from the unobservable darkness. This southern giant mirrors the grand architecture of the northern sky, stretching across the constellations of Horologum and Reticulum. A sprawling celestial empire known as the Horologum-Reticulum Supercluster spans an astonishing 550 million light-years. It is a titan of the southern hemisphere, a complex web of galaxy clusters and filaments that serves as a crucial counterweight to the great northern structures like the Sloane Great Wall. Its existence confirms a profound symmetry in the cosmos, proving that the universe's architectural ambitions are not confined to one direction. When we map the distribution of matter, we must look everywhere to avoid a skewed perspective. The study of this supercluster is a vital correction to any potential northern bias in our cosmic senses, ensuring our understanding of the large-scale universe is truly representative. Within its immense borders, astronomers have identified numerous massive galaxy clusters, each one a dense knot of hundreds or even thousands of galaxies, all bound together by the relentless pull of gravity. These clusters are not isolated islands, but are connected by faint bridges of galaxies, tracing the invisible scaffolding of dark matter that defines the supercluster's true shape. Observing the Horologum Reticulum Supercluster is like finding a familiar city on a new continent, its streets and neighborhoods laid out according to the same fundamental blueprint that governs all cosmic structure. This southern giant demonstrates that the laws of physics and the initial conditions of the universe conspired to create immense formations in a consistent, predictable pattern across the entire observable sphere. Its presence in our maps completes a more balanced picture of the cosmic web, reminding us that the universe, in its grand design, strives for a deep and underlying uniformity, even as it builds structures of breathtaking scale and complexity. What other mirrored giants might be waiting in the uncharted depths, ensuring the cosmos remains balanced in its magnificent, sprawling design? Far to the north, a faint and ancient wall of galaxies stretches across the constellations of Lynx and Ursa Major. This Lynx-Ursa Major supercluster is a cosmic fossil, a sprawling complex observed at such a great distance that we see it as it was when the universe was only half its current age. Its light has traveled for over 5 billion years to reach us, offering a direct snapshot of the cosmos in its more youthful, formative era. This is not a fully settled metropolis like our own local superclusters, but a grand construction site, a place where the fundamental architecture of the universe was still being bolted into place. By studying its size and the specific way its galaxies are clustered, astronomers can trace the timeline of cosmic assembly. They can see how the subtle ripples of density from the Big Bang were, over billions of years, amplified by gravity into this recognizable wall. The configuration of its galaxies tells a story of gradual accumulation, a slow, relentless gathering driven by the invisible pull of dark matter. This distant giant is a crucial piece of evidence in the timeline of cosmic evolution. It shows that the processes which built our nearby universe were already well underway in the deep past, operating with the same fundamental rules across vast stretches of space and time. The Lynx-Ursa Major Supercluster connects our modern, local cosmos directly to that ancient epoch, revealing a continuous thread of structure formation that has woven the entire cosmic web. What other formative blueprints from the universe's adolescence are waiting to be discovered, frozen in the deep field light from other distant walls? Emptiness is not a distant abstraction, but a feature of our own galactic neighborhood. The Microscopium Void is a spherical region of space, relatively close at just 75 million light-years away, where the expected population of galaxies is conspicuously absent. This is not a perfect vacuum, but its density is so significantly lower than the cosmic average that it qualifies as a genuine void, a local pocket of nothingness. While it is far smaller than the colossal Boots Void, its proximity makes it a crucial laboratory. The gravity of this emptiness is just as real as the gravity of a cluster. Because there is so little mass within the Microscopium Void, it exerts a weaker gravitational pull on its surroundings. This creates a subtle but measurable effect on the motion of nearby galaxies, including our own Milky Way. We are not just being pulled toward the Great Attractors, we are also being gently pushed away from the great emptiness. Think of it as a cosmic tide, where the water recedes from the shallow areas and flows toward the deep. The presence of this nearby void helps to calibrate our cosmic maps, giving us a clearer understanding of the various forces that guide our journey through space. The Microscopium Void serves as a perfect miniature, a microcosm of the vast, dark bubbles that define the sponge-like structure of the entire universe. It reminds us that the grand cosmic web of filaments and walls is defined as much by its profound absences as by its brilliant gatherings of light. If such a clear void exists so close to home, what other subtle empty regions might be subtly shaping the flows of galaxies just beyond our current resolution? This diffuse cloud of galaxies drifts through the constellation of the hunting dogs, a celestial gathering that defies simple labels. The Cain's Venatici cloud is neither a dense, brilliant cluster nor a profound void, but something in between, a sprawling, loose association of galaxies. It is a cosmic neighborhood, a collection of island universes that feel each other's gravitational presence without being bound into a tight-knit community. This cloud is part of our larger home, the Virgo Supercluster, and within its gentle borders reside some of the most famous galaxies in our sky, including the stunning Whirlpool Galaxy and the radiant Sunflower Galaxy. These are not isolated beacons floating in a perfect emptiness, but members of a local group on a grander scale, connected by the subtle, invisible threads of dark matter. The existence of the Cain's Venatici cloud reveals a crucial truth about the universe's architecture. It is a hierarchy of structure. Reality is organized like a set of nesting dolls, from single, isolated galaxies to loose clouds like this one, to dense clusters, and finally to the immense superclusters that form the continents of the cosmic web. This cloud is a perfect intermediate step, a tangible example of how matter gathers at every conceivable scale. It shows that the cosmos is not a simple binary of crowded cities and empty deserts, but a continuous spectrum of density, with every possible level of congregation represented. What other diffuse associations are woven through the darkness, forming the quiet suburban streets that connect the brilliant metropolitan hubs of the universe? Drifting through the Leo group of galaxies, a perfect circle of primordial hydrogen gas tells a story of what might have been. This is the Leo ring, a colossal structure 3 times the size of our own Milky Way, yet it contains almost no stars. It is a ghost, a vast cloud of pristine material that has somehow survived for billions of years, orbiting 2 massive galaxies as a silent, untouched relic. While most gas in the universe has been cooked into stars or blown away by galactic winds, the Leo ring remains a frozen sample of the raw material from which all galaxies are built. Its discovery was a triumph for radio astronomy because this ring is almost completely invisible in optical light. It does not shine with the brilliance of newborn stars, but instead whispers its presence through the faint radio waves emitted by its cold hydrogen gas. By tuning their instruments to this specific frequency, astronomers were able to map this ethereal structure for the first time, revealing a perfect loop of untouched fuel. Why has this immense cloud never ignited into a brilliant circle of stars? The answer lies in its delicate balance. The gas within the ring is too diffuse, its particles too spread out to collapse under their own gravity and trigger the chain reaction of stellar birth. It exists in a state of peaceful equilibrium, a sleeping giant of potential that has resisted the violent urges of cosmic creation. This makes the Leo ring a unique cosmic laboratory. By analyzing the chemical composition of this gas, scientists have found it is remarkably poor in heavy elements, the metals forged in stellar furnaces. This confirms its primordial nature, a direct link to the early universe before multiple generations of stars had enriched the cosmos. Its very existence challenges our understanding of stability. How could such a vast, delicate structure endure the gravitational tides and shocks of a dynamic galaxy group for so long? Its survival suggests that certain regions of intergalactic space can remain calm backwaters, preserving ancient conditions against the odds. This fossilized cloud offers us a pure, unaltered glimpse into the base state of the cosmos, the fundamental hydrogen from which everything we see was ultimately sculpted. What other pristine reservoirs of this primordial gas might be hiding in the darkness, waiting to reveal the untouched ingredients of reality itself? This delicate ribbon of gas is a scar from a cosmic collision happening right next door, stretching for more than 500,000 light-years across the southern sky. The Magellanic Stream is a long, shimmering river of hydrogen torn from our galaxy's two largest satellite galaxies, the Large and Small Magellanic Clouds. As these smaller galaxies swing around the Milky Way in a slow, gravitational dance, our much larger galaxy's immense tidal forces act like a relentless hand, pulling and stretching them. The stream is the visible evidence of this violent interaction, a trail of stellar debris left behind like crumbs from a celestial meal. It is a local, real-time demonstration of the same forces that build the vast filaments of the cosmic web, but playing out on a scale we can observe in intimate detail. By studying the chemistry and motion of this gas, astronomers can trace the history of the Magellanic Cloud's orbits and predict their ultimate fate. They are likely destined to be completely torn apart and absorbed by the Milky Way, their stars and gas becoming part of our own galaxy's halo. This ongoing destruction reveals the life cycle of satellite galaxies, showing how large galaxies grow over time by cannibalizing their smaller neighbors. The Magellanic Stream is a bridge not just of gas but of understanding. It connects the grand, theoretical processes that shaped the early universe to a dynamic event unfolding in our own celestial neighborhood. It proves that the architecture of the cosmos is not a static monument, but a living, breathing entity, constantly being reshaped by the fundamental force of gravity. If such dramatic changes are happening so close to us, what other subtle transformations are occurring across the local universe, quietly reshaping our galactic home? This river of gas from our galactic neighbors is not the only stream flowing into the Milky Way. A far more mysterious cloud is racing toward us from the void, a rogue wave of hydrogen known as the Smith Cloud. Discovered by astronomer Gail Smith in the 1960s, this colossal structure is a high-velocity cannonball of gas, 11,000 light-years long and 2,500 light-years wide, hurtling directly toward the plane of our galaxy at over 300 kilometers per second. Its trajectory is a perfect arc, a return path that suggests this is not its first encounter with the Milky Way. Detailed observations from radio telescopes, especially the Green Bank telescope, have revealed its composition, and the findings are a puzzle. The cloud contains heavy elements like sulfur, which are forged in the hearts of stars and scattered by supernova explosions. This crucial detail tells us the Smith Cloud is not a pristine, intergalactic wanderer. It is the shredded remnant of a dwarf galaxy that ventured too close to our own, its stars torn away by tidal forces, leaving behind this ghostly ribbon of its former gaseous body. In approximately 30 million years, this cosmic fossil will slam into the outer reaches of our galaxy's disk. The collision will be a spectacle of pure cosmic force, a silent, slow-motion impact that will compress the gas, triggering violent shockwaves throughout the spiral arm. These shockwaves will ripple through vast reservoirs of dormant hydrogen, squeezing them until they reach a critical density and ignite into a brilliant firestorm of new star formation. The Smith Cloud is essentially a delivery of fresh fuel, a shipment of raw material that will one day birth millions of new suns. This ongoing accretion process is how galaxies like ours avoid stagnation. They are not closed island universes, but dynamic engines that continue to grow by consuming smaller neighbors and capturing gas from the intergalactic medium. The cloud's journey is a small-scale, local echo of the vast flows of matter that built the cosmic web itself. It demonstrates that the architecture of the universe is not a finished monument, but a living structure still under construction, with our own galaxy, an active and evolving participant in this endless cycle of creation. This profound emptiness is not a distant phenomenon, but a presence we live beside. Right on our cosmic doorstep lies the local void, a vast and underdense region of space that directly borders our own local group of galaxies. While we often picture our Milky Way and Andromeda drifting through a typical neighborhood, the truth is far more stark. We are nestled against the edge of a colossal bubble of near-nothingness, a void whose low density exerts a subtle but constant pressure on our entire local universe. The pioneering work of astronomer R. Brent Tully, who also helped map the Laniakea Supercluster, has been crucial in charting the contours of this local emptiness. His detailed maps of galaxy motions reveal a clear pattern. Our local group is not just being pulled toward the mass of the Virgo cluster and the Great Attractor, we are also being gently pushed away from the local void. Think of it like a cosmic game of tug-of-war, where the dense regions pull and the empty regions shove. This void is not a perfect vacuum, but its gravitational weakness is its defining feature. With so little mass inside it, its gravitational pull is feeble, creating a relative high-pressure zone around it. Matter, including our galaxies, naturally flows away from this low-density area and toward the gravitational wells of denser clusters. This makes the local void an active participant in shaping our cosmic journey. Its presence grounds our understanding of the cosmic web in a deeply personal way. We are not merely observing a sponge-like structure from a distance. We are living within its texture, with one side of our home pressing against a wall of galaxies and the other facing an immense, quiet expanse. This nearby emptiness is a constant, humbling reminder that the grand architecture of the universe is defined as much by its profound absences as by its brilliant gatherings of light. The void next door completes our local map, providing the final piece of context for our place in the cosmos and framing the ultimate question of what other unseen structures might be guiding our path through the darkness. Our journey across 30 cosmic giants, from the Hercules-Corona Borealis Great Wall to the void at our own doorstep, reveals a universe that is anything but random. It is a structured, dynamic, and evolving architecture, a grand tapestry woven from the invisible threads of dark matter and stretched by the mysterious force of dark energy. Each titanic wall and every profound emptiness tells a part of the same epic story, a narrative of cosmic evolution driven by the relentless force of gravity. These structures are not silent monuments, they are active participants in the life of the cosmos, challenging our simplest models and forcing us to continually rewrite our understanding of reality. As our telescopes peer deeper and our maps grow more detailed, we stand on the brink of discovering even more incredible features, pushing the boundaries of knowledge toward horizons we cannot yet see. So the next time you gaze up at the night sky, remember that you are not just looking at scattered points of light. You are witnessing the brilliant nodes of a vast, interconnected web, a cosmic city of breathtaking scale and beauty. We are a small part of this magnificent architecture, and its story is our story too. What cosmic wonder captured your imagination the most? Share your thoughts.